Welcome back, ladies and gentlemen. I would like to now invite Dr. Sheng Bau from South Africa. He'll be delivering his talk on metric spaces over groups. Dr. Bau, can you listen me? Can you hear me?
Yes, I can. Greetings, everyone.
Good evening, Professor Sheng Bau. It's Surprise here.
Yeah, this is morning here, and
okay.
Very nice to. It could have been nicer if I managed to get there in physical form. more than 3 years ago, Sana Javed, she's now professor, I think, asked me to give a course in this CIMPA workshop.
Yeah, exactly.
And I agreed, and I was really thinking I could come in person.
Yes, exactly. Yeah.
And until today, it was my fault. I didn't notice my passport has expired during the COVID.
Mm-hmm.
I have applied for passport in late November and late September, and this is November now, and still haven't got my passport, so I wasn't able to attend. So my apologies to everyone, and greetings to everyone. Very nice to be here.
Yeah, it's quite unfortunate that you could not make it to come here, but thank you so much for giving this opportunity to have these online lectures. Thank you very much.
Thank you. Are you Dr. Sarfraz?
Yes,
Ahmed?
I am. Yeah, I am.
Yes, nice to see you.
Same here.
So I will now start. I was thinking to attend Li Ping's lecture, Professor Yuan's lecture, 1 hour earlier than me, but I wasn't able to see the lecture in the room.
Yeah, I will send you. I will send you. Okay.
Yes, thank you. So 4 parts in my course, and I would like to invite everybody to interrupt me anytime between. Don't wait until the end, because this is a workshop. This is about dimensions and the 4 parts. The first part is topological space. It is a basic part of this whole course, and inclusion is done because this is nice to see everyone. So everybody who studied topology or metric spaces, remember that the 2 oldest topics in topology were theory of continua, which is about what Cantor did for intervals and in real numbers. And the other one is dimension theory. So this is, in fact, oldest branches of topology. These were motivated by the following simple question. What is a curve? Number 1 question. Number 2 question was usually asked by undergraduate students. Number 1 question is also asked by undergraduate students when they do calculus or algebra. Number 2 question is, what do you mean by independent variables? If you have an equation, for example, equation involving variables x, y, z, and so on, it could be finite, it could be infinite. What do you mean by independent variables? These led to serious considerations by many people, many famous mathematicians in history. For example, with regard to what is a curve, Euclid did nearly 3,000 years ago, more than 2,000 years ago. He systematically studied in his elements straight lines, triangles, line segments, polygons, circles. And some of these are examples of curves. And during the Renaissance period in Europe, Descartes and Fermat introduced what is meant by coordinate systems into mathematics, and which did a lot in mathematics and outside mathematics. Then these questions of independent variables and things come up. These questions came up because now we are studying curves through equations. For example, what is a plane curve? And it was originally understood that if you have an equation fxy equals 0, which relates somehow two variables x and y, then every point, every pair of coordinates that satisfies such an equation is called a plane curve. And this was actually generally accepted by school teachers and lecturers of lower undergraduate courses such as calculus. But even if you require f to be differentiable, a differentiable function, then this actually covers a lot because every closed subset of the plane can satisfy such an equation with differentiable f. So the curve is not quite what people thought. And we also considered in analysis, in calculus or analytic geometry, parametric curves when you have a parameter running in a closed interval, and then and univalent functions, these y, t, and x, t are functions, univalent, then such curves can occur, and these are also plane curves. Therefore, the definition, because of every closed subset of the plane, including the whole plane, can satisfy such an equation for even differentiable f. This definition of the pair of coordinates satisfying an equation is not satisfactory from topological point of view. Therefore, a topological definition is needed for what is a curve, for a curve. And Piano or Jordan gave a definition which says that any continuous image of a line segment is a curve. And this doesn't satisfy anyone also, because Piano produced the space filling curve, which I'm going to give in Hilbert's version. So this is the Hilbert's curve in the initial and the after three iterations. And you can see that this can be iterated further. And Hilbert proved that this is a continuous image of a line segment, and every point inside the square is on the curve, which means the image of this continuous image of this line segment covers the square. This shows also that Jordan's definition of a continuous image of a line segment, regard that as a curve, is not. And such Jordan curves are called Piano continua. You can actually fill the closed n cube in n-dimensional Euclidean space by a continuous image of a line segment. So the linear algebraic dimension 2 was not vital in this question. This even led to the serious question that whether or not the linear algebraic dimension of a Euclidean space is a topological invariant. Topological invariant means if you have a homomorphic space to a given space, then the parameter, which is called dimension, is equal for homomorphic space. Homomorphism is a bijective continuous mapping whose inverse is also continuous. One should not really, beginning students should not really think that, well, if you have a continuous mapping which is bijective, the bijective mappings always have an inverse, then its inverse is automatically continuous, which is not true. There are examples. And it was Brouwer who completely resolved this problem, this question in 1911. And he introduced a whole lot of definitions of a dimension of a topological space. And currently the widely used topological dimension concept was introduced by Lebesgue, also in 1911, using open covers. We are going to do that in this session. Lebesgue was the only mathematician who understood, probably even until now, very few mathematicians who really understood what the dimension of a topological space is. Of course, there are other dimensions which are not even integers. We are not going to do those. And the first proof of the Lebesgue's theorem was actually given by Brouwer in 1913. He also managed to prove his theorem in 1921. So most of the definition of a topological dimension of a topological space was given by Poincaré using something called an inductive dimension. He gave at least two inductive dimensions of a good topological space. We will clarify what is meant by good, because it doesn't really, his definition doesn't really work for all topological spaces, especially the pathological topological spaces, which people are really fond of studying, but I think we will not talk about that because I might offend someone. Brouwer gave a rigorous proof of Poincaré's idea. And our treatment here is due to Menger and Carl Menger and Urysohn. English people pronounce this name as Urysohn, which is not correct. It's Urysohn in Russian or in Russian language. They shouldn't say Ukraine, it's Ukraine. Anyway, this is where the war is now. So we're going to brief through definitions of these inductive definitions of dimensions. Urysohn's definition of a curve was one-dimensional continuum, and this is topologically satisfactory. This, of course, covers Hilbert curves and so on. So Urysohn's main result was to prove that if you have a compact metric space, then what is meant by small inductive dimension is equal to the upper inductive dimension, and which is equal to the Lebesgue dimension using open covers. We are going to cover this proof. Menger also proved that every curve is homomorphic to a subset of a three-dimensional Euclidean space. Look at that. So the curves are actually subsets of a three-dimensional Euclidean space. So we are going to use small int and with uppercase I with int, and dim as the Lebesgue dimension, but small int is a lower inductive, the small inductive dimension, and the uppercase I int as upper case inductive dimension. It's not lower or upper, it's in the all. So inductive dimension lower int is defined to be in the following inductive manner. So let X be a topological space if we define the lower int of empty set to be -1. And we define that if for every point in X and each open set containing X there exists an open set V, so that its closure is also contained in U, and the boundary of this V is at most n-1, then we define the inductive dimension of X to be at n. This is an inequality, definition of an inductive definition of an inequality. The lower end is not exceeding some non-negative integer and -1, because -1 is defined similarly. And then if 1 is true for n -1, true for n, and it is false for n-1, then define the lower inductive dimension of topological space X to be n. This definition is works for all topological space. You can see there is no qualifier, no quantifier in front of X. If 1 is false for every natural number n, then we define the lower inductive dimension of X to be infinity. And this is ambiguous. This infinity sign is ambiguous. You know that when calculus lecturers say this is something we're extending real numbers by adding plus infinity and minus infinity into and then expand. That is not good, because this symbol is ambiguous, undefined. We are using it as an undefined symbol. We are not pointing to one infinity and we say that it is that one. We are not saying that. So you have to be careful if you're an undergraduate student when the lecturer says this, we are adding this plus infinity to. That is just actually something wrong, something false. Here, this definition works for every topological space on one hand. On the other hand, it uses only the concept of an open set. Therefore, it works. Because topological spaces are defined by specifying open sets according to 3 axioms. So in the X is well defined. This is point number 1. Point number 2, you can easily prove that because it is defined using only open sets, and homomorphic spaces, the open sets of the two homomorphic spaces are in bijective correspondence to each other. Therefore, for homomorphic spaces, the lower end is equal. If 2 spaces are homomorphic, then their lower end is an integer, which are equal. The least of these is -1. We can't say it's non-negative integer. So this is proved. Third point to remark here is that condition 1 is equivalent to the statement that X has a base such that for every element of the space, the lower inductive dimension of that boundary of that open set is at most n-. So the condition 1 can be replaced by a condition using neighborhood and boundary. And now, if you have a dimension, for example, linear algebraic dimension of a vector space, if you have a subspace of a vector space, then its dimension cannot be larger than the dimension of the ambient space, even before defining whether they have finite bases and things like that. You can what this says is that monotonicity is a legitimate requirement for a well-defined dimension of a topological space. The monotonicity means that if X is a subspace of Y, then the dimension lower end of X cannot exceed the lower end of Y. Some subspaces cannot have larger dimensions. We will come to this again and again, this monotonicity. And this can be proved, and its proof is trivial, utilizing the definition which we just gave. Is a Urison's, Menger and Urison's definition, Urison. So let us consider, of course, you consider the vector spaces, and then you can find this all agrees with the linear algebraic dimension. So let us consider some space which is not a Euclidean space. So let us consider a simple such space, which is the one-dimensional circle. We will have to prove that its lowering dimension is 1. So for every point in this space, there exists a neighborhood which is an open arc. This is a fourth law in topology. And you know that the open arc, the boundary consists of 2 points, whose dimension is 0. Therefore, we have by the definition of lower end, the lower end of S1 is at most 1. Now, if you assume that it is 0, then that it must have an open set whose boundary has dimension -1. But boundary is equal to -1 is only true for empty set. Therefore, the set must be both closed and open. This is a contradiction. So the lower end of one-dimensional circle is not 0, and it is at most 1. Therefore, it is 1. This proof can be similarly worked, and if you are looking for exercise questions, now these all have low end 1. This is a very interesting example, which I always give first-year students when I teach calculus, beginning calculus. I ask how many different types of intervals are there with the students, and then students usually quickly answer that there are infinitely many different intervals on the real line. And when I correct them, because I asked how many different types, and then they work for some time, and then they get some of these right. Of course, this is not all, because an interval as a subset of real line also includes empty set and single point set as well, because they also satisfy the condition for an interval. Interval means that if you take any 2 distinct points, then everything in between is also in the set. And this is true for empty set, because you cannot take any point out of empty set, and therefore the conclusion is true. And if you have 1 point set, you cannot take 2 points out of it. Therefore, it is also, conclusion is also true. Plus those 2, there are altogether 11 intervals as a subset of real line. These are listed here. There are 9 here, plus empty set and single point set. I usually give this to beginning undergraduate students. 11 intervals, 11 types. This type is not defined. You have to really call what is the type. Type means that how many ends it has and which ends it is including and so on. So for example, the number 1, it has 2 ends, but both ends are not included. The second one is it has 2 ends, but the left end is included, the right end is not included. These are called types. And this needs a definition, and therefore it's not undefined. But anyhow, this is it. And you can easily prove also that if the lower in the inductive dimension of a topological space is 0, then it is a disconnected space. You have to really know that this doesn't mean that it contains a countably infinite isolated points. No. We're not saying that. We're saying that it is disconnected. Disconnected, you recall that from topological definition that it can be put into the union of non-empty sets, both of which are both open. That is called disconnect. So, which means that if you have any set X, even if its cardinality is much higher than the continuum, but if you have discrete topology, then its dimension is 0. And similarly, you can prove this. We have just said it actually. If every point has a neighborhood who is both closed and open, then this topological space has definitely dimension 0. This is a necessary condition. Similarly, counter set has cardinality continuum. We know that. But counter set has lower in dimension 0. Just like its Lebesgue dimension is also 0. You recall from topology. This is proved here because I have included this very detailed proof into these slides. I'm not going to spend time on it. You can read through it. Any question we can discuss. It's a very beautiful proof due to Menger and Urison independently. Now here is a statement here. This is, we define all mappings from X to Y as X superscripted, Y superscripted by X. So we're talking about all the mappings from the natural numbers to binary 0 and set. So we are, this is the same as every value for every natural number, and the value of function is 0 or 1, which means that we're going to list the sequence whose values are only 0 and 0 and 1. This is a 0-1 sequence of infinite length. You can see that this is there is a homomorphism from this topological space to the counter set. To a subset of the counter set. Therefore, we can say that the counter set is actually a universal space with dimension low into 0. So if X is a separable metric space and its dimension is 0, it's a low inductive dimension is 0, then there is a homomorphism from this space into a subset of the counter set C. This means that every separable metric space with lower inductive dimension 0 is contained as a homomorphic, contained as under homomorphism as a subset of the counter set, which means that counter set contains all such metrizable topological spaces with lower inductive dimension 0. Under this meaning, we say that counter set is universal with dimension 0. I have to be careful how much time. Oh, okay, 1 hour, 45 minutes, fine. Now, similarly, we can prove that. Here we prove the inequality. The n-dimensional Euclidean space, the n-dimensional Riemannian space, which is denoted by S superscript n, and the n-dimensional unit cube, their lower inductive dimension is not greater than n. And we're going to prove that these are all at least n as well. And then we establish that this n is actually the Lebesgue dimension, this n. We're not, because that one doesn't have any linearly independent, you cannot, this is not a vector space. So, of course, there might be one bijective mapping between them and then, but this is not the linear algebraic dimension. This is the Lebesgue dimension we're talking about, the topological dimension. We have already shown that the real line and the unit circle and the closed line segment from 0 to 1, their lower inductive dimensions are all equal to 1. So this begins the induction. So for every x, every real number, there is a neighborhood U. Actually, this is for any point in one of those three. That one is meant to be just an outlined one. There is a neighborhood U which with an open set homomorphic to this is R minus 1, Rn minus 1. I think there's some error here. I'm sorry about that. So we're looking at Rn minus 1, S to the n minus 1, and 0, 1 to the n minus 1. I'm sorry. So by the inductive hypothesis, the lower end of Sn minus 1, for example, is n minus 1. I can't see the bottom of my, oh, it's covered by that. So we are only considering one of them, this one, the n-dimensional space. And this is by inductive hypothesis is true. So the conclusion of the theorem is true by induction. This Bloom cannot put this thing on the left. So if an Euclidean space, the Riemannian space, or the n-dimensional unit cube, or a unit cube has Lebesgue dimension n, then their low end dimension is also. Now here, we recall a definition from topology by when we call two subsets of a topological space separate. When, under what meaning we say that two subsets of any given topological space separate. So let the A, B be subsets of a topological space. And if each of them has an open subset of X containing them, so that these open subsets are disjoint, and we look at the common boundary as L. So you take the complement of the open subset for A and the complement of the open subset for B. Their intersection is we denote it by L. Then L is called the separator between A and B. This is one of the definitions of separation. There are other definitions. I'm not going to go through all of it. This is a definition which is quite liked by Professor Yuan. So people who do convex geometry, discrete geometry, because they want to have two convex sets separated if there is a hyperplane which separates them. And here, this is probably a hyperplane if you are in a convex setting. So let X be a topological space, and we assume that its lower inductive dimension is at most n. We're not assuming that. We're saying that this is true if and only if there is a closed set and a separator such that this separator has dimension n minus. Every closed set is a there. For every closed set, something missing here. What happened to my slide? There's a separator with dimension n minus, at most n minus 1. We are separating X from P, I think. So this theorem is false now because the statement is incorrect. So we prove, we assume that the low inductive dimension of topological space X is at most n, and we're going to reduce the right side. So let X be a point and B be a closed set. Closed set not containing X. Then there is a set meant to be open set such that B and the closure of this open set doesn't intersect. This open set contains X. X is in any element, and there exists an open set containing X such that this is true because B is closed. By the lower definition of the lower inductive dimension, there exists an open set so that contained in this open set, such that this X is a member, is an element of this open set, which is contained in the open set, X, such that the boundary of U has dimension n at most n minus, because we are assuming that this dimension is at most n. Then we can prove that this L, which is the boundary of open set U, is a separator of V and actually V bar and B. So here we something is missing, but we are separating X from B. So we assume that for any point X in the topological space X and any closed set not containing it, there is a separator L separating X from B. And we show that the lower inductive dimension of X is at most n. And let V be a neighborhood of X. Then V is open, therefore its complement in X is a closed set. Any way of putting this on the left-hand side? So there exists an open set. There exist open sets U and W. U contains X and W contains the closed set B. Such that because W is open, its complement in X is closed, and the closure of U is a subset of complement of W. The boundary of U is definitely contained in the closure because closure consists of the set and its boundary, union of the set and its boundary. And this is, we said, it is contained in the complement of W. And the boundary is the closure minus the set itself. One more equality. This is a subset of the complement of U. Therefore, boundary is contained in this, which is by our definition of a separator, which is L. And L has dimension at most n minus 1. This shows that X has lower inductive dimension at most n. And we will skip this. This is let X be a metric space and Z be a zero-dimensional separable subspace. This is the whole sequence of results which will work for all metric space, all metrizable topological space. What does this theorem state? Let X be a metric space of metric space and Z be a zero-dimensional separable subspace of X. Then for every closed set AB of X, which are disjoint, there exists a separator such that separator of A and B, such that this separator is disjoint from that subset. Let X be a metric space and Z be a zero-dimensional separable subspace of X. Then for every closed set AB of X with which are disjoint. Oh, what happened to my slide? Because I didn't type this. This is a repetition of this theorem, sorry. But the consequence is that the separable metrizable topological spaces then will be unions of zero-dimensional subspace. So this separator and this theorem leads to this corollary. And dimensions, lower inductive dimension is sort of additive in the inequality. It says that. So what does it say? Let XY be separable metric spaces with the lower inductive, the dimension. Let us for the moment say that it's just that dimension. Dimension of X is most M and dimension of Y is at most N. Then X union Y, the union space, is the union of these Z sub ij's, where I goes from one, I takes value 1 and 2, the J takes value from 1 to M minus 1 for I 1 and 1 to N plus 1 for I equal to 2. And each of these has dimension at most 0. And the union is the union of X and Y is the union of. In particular, if the union has dimension at most M plus N minus 1, or the lower inductive dimension of this is at most the sum of the dimensions of X and Y minus 1. There are a sequence of separation theorems. So let X be a separable metric space. Separable means there are at least 4 or 5 types of separability in topology. Here, the separable means that if you have any 2 distinct points, then there exists the open set for each of them, containing each of them, so that these open sets are disjoint. That is what we mean by separable. Separability 1, type 1. And if you have a separable metric space with dimension at most N and AB closed set, disjoint closed set, something also missing here. Then there is a separator L between A and B whose dimension is at most. We have X is decomposed into spaces Y and Z with Y having dimension at most N minus 1 and Z having dimension 0. Then by the second theorem, is before this theorem, there is a separator between A and B, which doesn't intersect this zero-dimensional subset Z, which is also metric subspace, of course. Hence, L is a subset of Y, and L has dimension at most N minus 1. This is the end of the proof. Next lemma extends the separator of a subspace to the separator of the space. What does the lemma say? X be a separable matrix, and Y be a metric subspace of X. And we assume that AB are disjoint closed subsets of X. UV are open sets, which this is now closed sets are separated by open sets containing them. This is type 3, type 4 separability, but metric spaces satisfy this. And the closures of these open sets are disjoint. Then for every separator M of U intersect Y and V intersect Y, these are the open sets in the induced topology in the subspace Y. There's a separator L which separates A and B in X, so that this separator intersecting the Y, the subset of M in the subspace Y. Second separation theorem. Let X be a metric space and Y is a separable subspace whose dimension is at most n. Then for any disjoint closed sets AB of X, there exists a separator L such that the intersection of L with the subspace is at most n. This is called the second separation theorem. There is a third separation theorem. The proofs are not included here. You should really go for proving this using the definition of a separator and the theorems we proved earlier. Third separation theorem states that X be a separable metric space with dimension at most n. Currently, we're talking about this lower inductive dimension defined by Poincaré and treated very well by Menger and Urisson. Then for every sequence of pairs of disjoint closed subsets of X. So this is a sequence of pairs of disjoint closed subsets. So each pair are disjoint. There exists a sequence of separations, separators L1 to Ln plus 1, such that these separators are disjoint. So if you intersect all of them, it's empty. Disjoint means that. Skip the proof. And we are going to use, to prove the next theorem, we're going to use Brouwer fixed point theorem, which is a beautiful theorem in basic topology, which you can teach for honor students. Brouwer fixed point theorem states that if you have a non-empty compact convex set, compact is closed, therefore this is redundant, this word. In the n-dimensional Euclidean space, and if you have any mapping, then that mapping has a fixed point. Of course, there are lots of fixed point theorems. There is Poincaré fixed point theorem, for example, is about the bounded complex. This is a compact convex set. Brouwer fixed point theorem is about compact convex set, mapping which maps the set to itself. And we denote the unit line segment by I. Therefore, the n-dimensional unit cube, closed cube, is I to the n. The n-fold Cartesian product of the unit segment. Let us consider a sequence of pairs of disjoint closed sets, which are opposite faces of. Remember that we call in an n-dimensional complex, we call a k-dimensional boundary in topology, in algebraic topology, a facet. But if this k is equal to n minus 1, the one less dimension, then we call it the face. So this is where the face is coming. Let Li be a separator between Ai and Bi, because these are closed, disjoint closed sets, because they are opposite faces. Then all of them don't intersect. Li is a separator between AI and BI. AI, BI are opposite spaces. By definition, there exists open subsets, BI and BI, UI containing AI and BI containing BI, such that the definition of a separator is Li is equal to the complement of union of UI and BI in the n-dimensional closed unit cube. Now we define halfway point. So define f sub I of x to be half plus this distance between x and Li, which is the infimum of distances of x to every point Li, which, because Li is closed, then this is actually attained by the minimum. And here we use this denominator, which is twice the distance of AI and x, plus twice the distance of AI and Li. Similarly, we define if x is in the complement of Vi, which is the one which contains the face Bi, and if x is in the complement of Ui, we define it similarly, but here there is a minus sign here. Then this is a well-defined mapping, and it is continuous. Distances are continuous, and then this is actually a rational function of sort of distances, because here we have this is an interlinear combination of plus. So this is a continuous mapping, and we have this here. Let me try to move this. I can't see that. If you can't see it, it's fine. But this bar is blocking my view. And then we define a mapping F by using the F sub I as component of order. Then this F is a continuous mapping because each component is continuous. If the intersection is empty, then for every x in the closed unit cube, f of the image of x is never equal to the vector which has each component just half. This is shown by the definition of f sub I. We are adding a small number on top of half in one case, and we're subtracting a small number which is smaller than half, positive number smaller than half in the other case. So the image can never be this vector. And we define the projection of the n-dimensional unit cube minus that point onto the boundary of the cube. So we are taking away a center point, and then we put a light source, and then we're projecting it onto the boundary. So every point in the closed unit cube is projected onto one point on the outside boundary, which consists of square faces, sort of. And we define mapping G by composite of F, and first act F, then act G. Then we have, you can actually verify that G of the image of AI is a subset of BI, and image of BI is a subset of AI. And G of the whole image of the whole cube is on one of these. So the image of the cube is on the outside faces. This implies that for every x in every point x in the cube, g of x is not equal to x. This is a contradiction to our fixed point theorem, which actually assumes that the mapping is continuous, I think, but there's some word missing in that. This completes the proof of the theorem. Theorem states that these separators of the opposite faces, the intersection is not empty, they intersect. I said something, they don't intersect. They intersect. After the proof, you can see that. And the dimension of n-dimensional unit cube is at most n. If this dimension cannot exceed n-1, then there would exist n-1 separators of the opposite faces with empty intersection. This contradicts the theorem. Therefore, we have proved that the lower inductive dimension of the n-dimensional closed unit cube is at least n. The conjunction of the two inequalities prove that this is equal to n. Actually, this will now imply that Rn, the n-dimensional Euclidean space and n-dimensional Riemannian spaces, they all have lower inductive dimension exactly equal to n, because we have there is homomorphism, for example, from there is the homomorphism. You can repeat this proof and you can get the proof. So this also showed that this is now coming to the Poincaré proof. This showed that the Lebesgue dimension of every Euclidean space, but in particular, every closed unit cube, if the upper index is number of iterations of the Cartesian product, these two numbers are equal, then if these two are homomorphic, then the number of iterations is equal. Namely, the Lebesgue dimensions are equal, if equal for homomorphic cube, and consequently for homomorphic Euclidean spaces and Riemannians. So this answers the question in the positive that Lebesgue dimension is, the lower inductive dimension is invariant under homomorphism. I usually take time is up.
Dr. Bau?
Yes.
Sorry to interrupt. We have reached to our time limit.
Yes.
So any questions from the audience?
We haven't even reached the Lebesgue dimension yet, so that's fine. So next time we will continue from there so that we cover at least something. We can even omit the last lecture because that is a very specific thing. Yes, please, question.
Yes,
no one interrupted me.
Sorry. Yes, any questions from the audience? Thank you so much. Thank you, Dr. Bau, for your valuable lecture. Okay, we have reached to the end of our session. Thank you, ladies and gentlemen.